call my tutor to see if
Yeah, sure.
she's with people.
Yeah.
How are you going?
I'm good. Yeah.
Congratulations on
Thank you.
the job.
Yeah. Yeah.
So you
It took age. I didn't even know you could apply for promotion. So I applied, and then someone told me we don't expect postdocs to ever be able to apply, but it's possible.
Yeah.
Yeah.
Oh, of course.
And I applied, and they were like, in chemistry, I don't think anyone has done it before in the last few years. At least in the last 5 years, I've heard of no one doing it.
T402, yeah, come in.
Yeah.
Hello.
But it's research only, so I keep doing what I want. It's great. And I supervise students. It's really good. It's really good.
Like in terms
Yeah. 12 hours in total. Plenty of time. Yeah.
Yeah, it means you can't escape me.
So guys, do you know where the rest of you are?
Not many people want to go into lectures.
They might be walking, I'm not sure.
They might be walking, yeah.
But it's still not permanent. It's paid on. I have to secure my own grants to get paid. Yeah.
Oh.
But it's getting there. It's getting closer.
Mine also said like 5 years compatible.
Yeah.
So next year I'm gonna actually.
Sounds good. Yeah. But I've been doing a really fun project. I'm putting a fuel cell on the drone.
Did you bring again your 3D?
No, someone took them from me this morning, someone else, so I don't have them today.
Oh.
They used them for a showcase in the campus.
Yes,
I was planning to, and then the lady was like, I told you today. And
Yeah.
So I didn't bring them. So we drove the drone yesterday. We flew it straight into a tree.
Drone?
Yeah.
Hydrogen drone?
We're planning to put hydrogen. We are waiting for the fuel cell delivery. It's really fun. I can show you later. And we're putting a fuel cell on the drone, and then the drone is with high temperature, loads of challenges.
Wow.
And so far, the fuel cell, we flew the drone, no fuel cell yesterday, for the first time. And it's so big, you're not allowed, we can't fly it. You need a professional pilot. And the drone went right into the bushes. But apparently they can fix it. It was really fun. We had to go in a field near Maroubra, near the beach, and just overlooking and just fly it. And yeah. My PhD student had to take the rest of the afternoon off. She was like too stressed. But they did really good. It was really fun. Like one guy just sat on the grass for 2 hours and just took photos and videos and our students, and they were like, this is nice.
You're doing fun stuff.
Yeah.
It's so fun. Oh,
Yeah. Yeah.
Okay, I don't think that it will have more people.
I think we're good.
We don't know. So I think we're already, 11:07. So,
Okay. Whenever you want.
Well, before actually introducing Quentin, we have reps from CEFSOC. So please over to you.
I'm just going to be the one talking. So my name is Rifa. I'm from the Civil Environmental Engineering Society. And we just wanted to let you guys know that the professional development camp ticket live. So if you guys are looking for jobs or internships, it's a really good way to learn more about how to write a good cover letter, how to get LinkedIn connections, and just network in general. The camp is going to be on the week 1 weekend of term 3, and you should have a flyer. Oh.
Just imagine it.
Yeah. Get the QR code, you can scan it for the tickets. So, thanks.
Okay. Everyone has the flyer?
Why is it so expensive?
Nicholas, do you have a flyer?
I have a flyer. Okay. Why is it so expensive?
Life is tough. These guys need to have a living.
We do it for free, we don't get paid.
Of course. So do we. So does everyone.
Okay, thank you so much, guys.
Thank you.
Are you also coming to my Edge 1400 lecture as well? Yes. 1400. Yes, 2 p.m. 109. Level 1. Yeah? Okay. Okay. Okay, so let me just introduce myself as well, because that's basically the first week that these students see me. So it's Cart, right?
Chris.
Chris, oh my goodness. Oh, same alphabet, right? Kind of. Chris, Tanya,
Nick.
Nick, Zach. Nice meeting you. I'm Ellie. I'm basically the lecturer for the second half. And thank you so much again. Apologies for Tuesday that I had to be in camera for diplomatic briefing, blah, blah, blah. anyhow, I record myself. Basically, we have today Quentin Meyer,
Yep.
Dr. Quentin Meyer from the School of Chemistry. Quentin is a scientist working on hydrogen fuel cell. He has been one of the best, or if not the most successful, but one of the best basically scientists here in Australia who is advancing the hydrogen fuel cells. And I know
I'm the
that-
only one who does it in Australia, so therefore I'm the best.
Yes,
Yeah.
yes.
Simplifies it right away.
So we are very, very honored actually to have Quentin with us. So Quentin actually will provide a lecture on hydrogen for transportation, the challenge and the way forward. And why I invited Quentin, the motivation basically, when we are talking about sustainability of transport, because the second half of this course is basically tailored designed for you as environmental engineering students. So we will learn about sustainability, we will learn about how to measure emission for transport, different transport use cases, how we can quantify the externalities, and also we will talk about sustainability frameworks, and then we have more people.
Wow, so many of you.
Yes. Lessons learned. Next one, actually, we should start a bit late.
Yeah.
No, that's
No
all
worries.
right. Not your fault. Just again, very briefly introducing myself. I'm Ellie. I'm the lecturer for the second half. And today we have Quentin. Meyer, Dr. Quentin is from the School of Chemistry, the best scientist in Australia that we have on hydrogen fuel cells. So Quentin, floor is yours, but please could you provide a bit of background about your journey?
Yeah, sure.
Where did you study?
Yep.
What did you study?
Sounds good.
When
Yeah.
did you move to Australia
Yeah.
and so on? Over to you.
So to give you guys a bit of background, so I got my PhD in England on fuel cells, so I got stuck into it very early on for a fuel cell company. And then after that, I stayed in London for 6-7 years. That was fun. And then basically my wife's visa was expiring in London, and she told me, hey, I've got Australian PR, do you want to come with me? I had no job at the time. I was like, well, whatever, I'll see what happens. At the time, there was very, very little talk about hydrogen in Australia. A few people told me, you're just going to get nowhere, and 6 months later, you'll be back in London. And then we stayed for 6 months. I was a consultant for a fuel cell company. And then the hydrogen roadmap pretty much came out at that time in Australia. So that made it a lot more exciting. And I learned there was one guy in chemistry who was launching a hydrogen fuel cell lab. And I was like, well, that's kind of cool because that's the only thing I know how to do in my life is fuel cells. So I was like, okay, I can work with him. And we've worked together for 7 years. Main thing we started was launching the fuel cell research from completely scratch. When I joined the lab, there was no table, no bench. It was as bare as it gets. And now we secured, I think in the last 2-3 years, I think 5 or 7 million of funding on fuel cells. We had 2 PhD students who I think graduated this year. And we keep doing a lot of fun research. And this course happened because a lot of people told me, well, there is not much going on in terms of curriculum on hydrogen by someone who actually works on hydrogen. So I've given different versions of this module with different focus to Ellie in environmental engineering, also to people in ChemEng, and to a few different courses when I change it. And my point at some point is that there is an actual hydrogen-focused curriculum. The uni said, that sounds fun, and then nothing has happened so far. So I'm giving you as guest lecture. I'm fully research-focused, so I just give guest lectures every now and then because it's fun, kind of interesting. And last time I recruited 1 PhD student. So if you guys at some point want a PhD, we offer 2 people when you guys are there. Yeah. So let me see. So hydrogen for transportation. So this is the group I work in. So we have very much chemistry focus, but we have a very, very strong engineering perspective for the group. So we don't just make catalysts like deep in the lab. We want to put them into something that actually works. So a big part of it is water electrolyzers, so how you actually make green hydrogen. Another part is hydrogen storage, so what do you do with your hydrogen? And the hydrogen fuel cell is the whole part I come in. And then over there, what do we have? Sorry, I'm going to change the slideshow setting for just 1 second. This is confusing my head. Duplicate slide view. Nope. Oh yeah, that's good. Yeah. So we've got material discovery. So when we make the catalyst, do all the research, then we characterize them, and then we actually commercialize them. So Professor Chuan Zhao got really famous, I think, 10 years ago because he made the world's most efficient electrolyzer in the world, and he commercialized it with a spin-out company. That has been taken over way ahead of at some point, but that's how he got famous. And the company who was funding him said, hey, do fuel cell. That sounds like fun. That's how I got hired, basically. So let's see what we've got. Is this going to play? Every time I play it, the video is getting older, so I'm not sure it's going to play today. Oh yeah, there you go. That's the world we live in on this side. And you guys probably heard a bit about hydrogen challenges, hydrogen economy. The idea of hydrogen is that we want to use the excess energy from solar panel or wind, and then turn it into hydrogen. And then this hydrogen, you store it, you convert it, and you can use it in fuel cell cars. And also you can use it to make green steel or lots of process way greener. But there is a very long journey to actually get there. So the point of this guest lecture is I want to tell you guys the challenges of the hydrogen economy. So big challenge is how much is it going to cost? What's the volume? What's the colors? And what's market is actually for hydrogen? And then, so I've tweaked this a bit today because there is so much more about transportation lately. So what type of fuel cell do you want to use for different application? Beyond just making a tiny fuel cell in the lab, that's me. How do you actually get to a device? Sorry. Be quiet, Teams. Okay, gone. And then hydrogen fuel cells for transportation. Okay.
Go to do not disturb.
Yes. If I knew how to, that would be helpful.
Go to your
I think I'm
Teams and
close. Mute all notification, that will do it, I think.
Yeah, let me help. Then here, just not this one. Do not disturb.
Okay, I've muted them anyway, so that should do it.
Yes.
Hopefully. Yeah.
As in,
Yeah. And so the real takeaway for you guys is when we come to what do you actually use fuel cells for in transportation, and are they green, and what's the alternative, and how they're going. And finally, I've got a bit of slides where I'm going to go quite fast, but just to give you an idea of what kind of research I do in fuel cell and the kind of things you can do. So let's see. So the hydrogen economy. So first thing, so all my figures are pretty much coming first from the internet. I'm really focusing on telling the story of what's going on and giving my perspective. So I've removed the reference, but you can find all of these anywhere you want. But the idea is hydrogen is a gas. It can be burned to produce high temperature. You can combine it with other elements. One of the challenges is you have very few amounts of hydrogen on its own. It's the world's most abundant element, but it's usually in other elements. So what do you have? You can compress it, you can liquefy it, you can disperse it. That's the characteristics. It has a lot of challenges. One challenge is it's extremely flammable. So it can catch fire, it can pretty much explode right away with your static electricity of your fingers. But that's something they've kind of sorted out mostly by storing it in big pressurized cylinders. Otherwise, it takes energy to isolate. It can be challenging to transport because it's a flammable gas. You can use it there's a lot of work to make safer systems. And the big part of it, that's what I've been preaching. You can use hydrogen fuel cells alternative to batteries. And there is also work on hydrogen combustion engine, which I'll touch base at the very end, which are sort of cleaner than regular engines. And you can use it in green. There's a lot of work for green steel. So instead of burning steel, you make it with hydrogen. That has potential as well. And there's a lot of different approaches. So I actually made this slide, I think, about a year ago for a small conference, and I got sick, so I couldn't make it. So you guys are the first one. The point of this slide is really what's going to happen in the next 30 years. So you guys have probably heard about net zero 2050, so hard to decarbonize. And the big point of this, and that's the one giveaway I want you guys to see, all the stats online are basically a guy with a crystal ball playing with Excel. So this is how it's looking like now. So there's basically very little. This is where we are. I think I need to move to next year. And this is where we are aiming to be. There is a long journey to get there. We are basically at the moment making somewhere in the, 20 or 30 million ton. We're aiming to be at 500 million ton in the next 30 years. So the challenge is enormous, 25 years, not even 30. Whether we'll get there or not, it's basically up to you guys to work in it, or up to me to work in it, but the big point is take the stats with a hint of with a grain of salt saying, you see a graph, you're like, is that actually gonna happen or not? So hydrogen economy. So one side is, okay, you make hydrogen. There is a range of different ways to make it. I'll get back on that. And then you store it in different methods. And then you use it for a range of applications. You can use it from, all of this is mostly on fuel cells. But there is a lot of other applications in terms of hydrogen green steel and a lot of different processes with hydrogen. So let's see. So the first thing about hydrogen, there's a lot of talks about different colors of hydrogen. So this started with about 3 colors when I started doing this. There is gray hydrogen, which is done directly, I think, from natural gas, so methane, which gets split in hydrogen and CO, and syngas. And most of the CO2 you emit just goes right into the atmosphere. So as environmental engineers, you can tell this is probably not a good way to go. But that's how probably 90% of the hydrogen right now is made. And then you've got blue hydrogen. Well, that's kind of better. Well, you still make the same process, but you try to trap all the harmful emissions underground. The problem you've got with that, if you want to make 500 million tons of hydrogen, you will end up with 500 million tons of CO2 underground. So that's not necessarily very scalable. And the best part is the green hydrogen, when you basically want to plug 2 wires into water, split it into hydrogen and oxygen. It looks simple. In practice, it's not. It's very expensive. So this has gone from 3 colors. And then a lot of companies say, I'm also making hydrogen with some fancy way. I also have a color. So you've got gray hydrogen, steam methane reforming, blue hydrogen procedure when you capture it, green hydrogen, which is the best. Turquoise hydrogen is a funny one, when you actually made hydrogen and physical carbon. So I spoke to a guy once, his theory was, yeah, we'll make so much carbon, we'll fertilize the ground, or we'll create mountains, because we're physically making blocks of carbon at the same time. That has potential, but again, you have to think of the scale of it. 500 million tons of carbon on the ground may not be something we actually want to deal with. And then brown hydrogen, so you just make coal. What you do with it, that's one I'm not really fond, I'm not really wild about. And then this kept getting worse and weirder and weirder. So I've put these slides to show you that my conclusion is the colors don't actually really matter. But that's another slide I saw. So all the companies are like, hey, I'm making more. So it goes to green. I think on the top side, it's kind of clean. So some people argued, hey, green hydrogen needs to be done only from renewable electricity. If you use a nuclear power plant or a coal power plant to make green hydrogen, it's not green because you've made CO2 or you've made waste that's going to last hundreds of thousands of years. So not very good. And then you have the best one is the solar-made hydrogen. And then it keeps going, and then it keeps going all the way to the worst ones, process making some fossil fuel, splitting methane. And then the news media go, hey, there's something going on here. So these are generally news articles about hydrogen. When you have all the different pictures, these are legit pictures that came out in the news, and that's when people online were like, hey, what's the deal with hydrogen? And so there is all the, the colors of hydrogen, expanding rate of decarbonization is hydrogen green, the colors of the hydrogen rainbow. And that's when I started to see people on LinkedIn who have weird titles like hydrogen P2X expert, hydrogen savant, hydrogen evangelist, when basically they've never even been remotely close to a hydrogen cylinder or to an actual device. But they need to make a living, so whatever. And then there's this paper I actually found much more interesting from this guy from 2022. What he kind of concludes is the colors don't actually really matter. What matters is how much CO2 you emit. So that makes a lot more sense. Forget about the colors and go, okay, we want to be from high carbon to near zero. Doesn't matter how you make it. What you want to be able to do is whichever technique you use, it can be made cleaner. How can you make your technique cleaner? A lot of people, they say, well, we should only make hydrogen with electrolyzers. The problem is the factories that have been making hydrogen with other methods, they can't just close business right away. It would take most of the almost systems have been designed to last 25 years. You can't just give up on that. So you have to find a way to make everything as clean as you can. And you can even aim for negative emissions. Say if you plant trees at the same time with whatever you've done, then you have negative emissions. Or you have much fancy way for it if you reuse your heat or your CO2 and move it in something else. So let's see where we are here. So I'm repeating a bit myself, but this is about the carbon footprint. So green hydrogen, no carbon, no GHS emissions, so no greenhouse emissions, perfectly clean, but it's only considered green. And we got flagged recently in a proposal because we forgot that when we applied for funding. It's only green, if the electricity is coming from renewable, from solar and wind. If your electricity is coming from coal, it's not green anymore because you're storing the energy of the coal into hydrogen. Then you've got all these in between, pink hydrogen, yellow hydrogen, I think maybe the one underground, and then it gets weirder and weirder and less emission. The problem we've got is, this is easy, well, let's invest all the money into green hydrogen. And what do we have here? Sorry, the same thing, yeah. So high carbon to low carbon. Again, you should invest into the green one. The problem of that is that looks pretty good. So see, I'm trying to get to the right slide I'm looking for. It's coming next, I think. I haven't done this presentation for a year. But basically, you have all the carbon intensity. So yellow, I think you have yellow hydrogen, which they called it. You could emit very low amount of carbon. That's from power. Black hydrogen is by far the worst. You emit a huge amount. And then you have all the fancy one on the bottom. So the interesting thing these days is there is what people call cleaner than green hydrogen. And the reason for that is there is an argument that nuclear may be cleaner than green. I'm not sold that this is actually true, because you're making nuclear waste that's going to last 100,000 years and will kill our, and you'll kill your descendants in a while. But right now, you could say it's green. And then there is all the weird ones. So there is talks about having, what is it, aqua hydrogen, I think oil sands, like hydrogen naturally forming underground. They exist. There is more and more work that say it's reported. The problem is someone is going to have to dig to actually find it and extract it. So that may not, and it's probably not, and it's probably in very tricky conditions, which they do probably upstairs more in civil. I work with people in civil engineering who work on that. But the point for me is, it may be completely green, but it may not be very easy to actually get it in a way that works. It may be blended with so much rocks or so much oil or so much stuff that on paper it looks good, but it's not going to quite get there. The problem we've got is that we can't just switch all our money to green hydrogen, because it's also the most expensive hydrogen to make. And the reason it's so expensive is we need to use a lot of electricity to make it, whereas brown hydrogen and gray hydrogen, which have been out for quite a while, they're way cheaper to make. So these stats are changing all the time. There's a lot of work to make this cheaper, but overall the problem is how do we make the cleaner one economically viable? So the point for that is doing a lot of research. So now that we've known the price and the cost, the volumes in steroid get worse. So that's what I was saying earlier. 95 to 100% of the hydrogen is currently gray and brown and some blue. And the green hydrogen, which everyone keeps talking about, only makes it in the 1%. And that's still evolving all the time. But we want to go from 1% green hydrogen to 500 million tons in the next 30 years per year. So there is a long way to go. And again, that's what the prediction is. As I told you guys earlier, this is a crystal ball. I'm pretty sure it's someone using Excel who makes them slightly fancier than Excel, but they pretty much predict, well, I've got this slope, it's going to increase by 2% every year, and there we go, we'll be completely fine in 2050. Well, we'll see where we go. Like, I've done a slide later when I show you guys what was predicted for fuel cells and what actually happened in the same time scale. And it's not quite as nice as that, but that's where we are very much aiming to be, and that's where there is tremendous amount of research onto actually doing this. So how much is the hydrogen going to cost? So I think this is green hydrogen. Right now, it's between $2 and $5 per kilogram. Per kilogram of hydrogen. And where we're aiming to be economically viable is somewhere in the $2 to $1. So the first part is making the electrolyzer more efficient. Well, that's purely from my side, that's from a chemist. And then there is a lot of part of making the electricity way cheaper. So solar panel electricity is somewhere in the $2 I think it's somewhere in that price. But according to online, that's what the number people are quoting, at the moment it's for a very, very tiny area somewhere in the world that they found electricity was this cheap. Most of the electricity is much closer to that. Again, you can make the device more efficient. This is expired at the moment. I was doing a paper recently. The stats we're aiming for an electrolyzer is somewhere in the 100,000 hours. So that's a lot more than that. So that's probably where we are in the 10 to 20 years. And then the interest rate, I don't even know what that is, but basically it's you don't actually buy your system. You are loaning it from someone, and then eventually it gets cheaper and cheaper over time. And this is where we are aiming to be. So there is a long way to get there. Another part of this is, well, we're making a gigantic amount of hydrogen, so where are we going to put it? So there's a lot of different fancy methods. That's the fancy method I call the metal hydride or chemical hydride. It's basically you make materials when you can physically store the hydrogen inside of them. The problem of that is that you typically need some energy to actually do that. It's not as simple as just liquefying or compressing it. So that one is potentially more challenging. It's feasible, it's very exciting, but in my mind, that may not take off right away because you need to scale up. There may be a lot of work in research labs when people have made very small, demonstrate, hey, I've made a very tiny cylinder. Well, I need a gigantic cylinder to do this. Is it feasible? Is it scalable? And another question for a lot of these new methods is how many times can you actually do it back and forth? Because we don't just want to use the hydrogen, we want to keep making it, refilling it. And for instance, I actually bought a tiny metal hydride cylinder on it, and it says on the website, infinitely rechargeable. On the cylinder, it says in Chinese, rechargeable 100 times. So there is still a way to, even for the ones you can buy, there is still a way to go to actually get there. And then, so there's different ways to make it. So this is just taking the common approach. So there is a few different ways. So the price of metal hydride is much higher. So you can compress it. That's the simplest way. That's what's mostly done. Liquefy it. You can make metal hydride. And you can also store it underground, which is a really interesting way of doing it. That's what I'm going to talk about. This one, no, next, the slide after that. So wait, I think the order of the slides may be wrong. Oh yeah. So about storing it underground, the idea of that, and that's very relevant to civil engineer as far as I know my friends who work upstairs, is we have depleted salt caverns or depleting oil fields. And well, it's depleted and was able to store gas really well. Could we just fill the thing with hydrogen? And that's very seriously considered. The question we still have is hydrogen is a much smaller molecule than the other gas that are stored in it. Is it actually going to work on large scale or not? At the moment, it seems like it has potential. There's been small studies, but this needs to be done at a very large scale to know if it works, to know if you lose hydrogen, to know if the hydrogen will mix with whatever is underground. And so that's still quite up for debate. Let me see for this one. Oh yeah, Australia is getting very excited by hydrogen underground. Mostly, I think, and Eddie can correct me on that one, because we've got a lot of salt caverns in Australia and plenty of space when you could do it. So there's a lot of different projects about generating hydrogen on this side, and then there's a lot of different places when you could store it within Australia. So I'm just going to go back a few slides. Oh yeah, so what does it say here? How will all this hydrogen be released? Oh yeah, now that we've stored it, and we found loads of ways to make it, how will we store it? Will it cost us energy or not? So liquid hydrogen, it's potentially a bit difficult because you need to go at very low temperature, so minus 253 degrees. So that you need energy to even store it. And then you consume a little bit of energy. So the physical methods, you probably need some energy. So compressed hydrogen, you don't need any energy. You just open the cylinder, it vents out. And then you have the weird methods that cost more and more and more energy. I think this one, it's not water splitting, it's water cracking. So at very high temperature, you can actually split hydrogen into water into hydrogen oxygen. At 1000 degrees, that will cost you 140 megajoule per kilogram of hydrogen. So that's not what we want to be doing, even if it's conceptually very interesting. In practice, it's not. People are not going to invest in something that consumes an enormous amount of energy to just release the hydrogen that you spent a huge amount of energy to even make. So now I'm going to go back a few more slides after this. Oh yeah, how will the hydrogen be transported? So now that we've made all this hydrogen, where do we actually go from there? So someone wants to use it. Say in Australia, we make a lot of hydrogen, we want to sell it to Japan. So there's been a project, I think, when they put hydrogen on a boat, there hasn't been a great amount of talk of what happened with the project. I've heard rumors that it may have leaked out because it was on there was a massive boat filled with hydrogen, and that was debatable whether it worked. The other way, and I've seen an action movie, I think, with Nicolas Cage, when there is a hydrogen cylinder on a hydrogen tank on the highway blowing up, is basically just filling massive trucks with hydrogen and transporting it that way. That is probably going to play a part in it, but it's most likely not going to be the way to go to do it at large scale safely. What's way likely are the pipelines. So pipelines, we've been using them for a long time. We know exactly how they work. We know they don't leak, so that's a good step. And also, the plan, I think, for some of the pipelines is gradually increase the amount of hydrogen in the pipeline. I think they're planning to increase to blend hydrogen and nitric gas, get you to 5%, 10%, I think even 20%, see how they behave with the boilers, with the systems, and eventually there'll be pipelines that are just hydrogen focused. That will cost a huge amount of money, but it's something that we know exactly, we know how to do it. And that's a big part of this is, if we want to do this in 30 years, it's hard if you start to invent technologies right now. They won't reach that in the time you're aiming for. But mostly the key away from this is pipeline is most likely be the way to go. So now there's something called hydrogen valleys. So I've added a few more recent slides on this. Sorry, the font is a bit tiny. But the idea of a hydrogen valley is the people before were saying, okay, I'm going to make my electricity in Canberra, then I'm going to have a huge pipeline, a huge cable going to Perth, and then I'm going to ship it to Singapore. And then people looked and like, that's not going to work because it's going to be so expensive, it doesn't actually make any sense. So now what people want to do is make it where you want to use it. So you have a solar plant or wind farm that makes hydrogen, and it's right next to the factory that's actually using the hydrogen. In practice, and obviously underground that you have a massive well when you store your hydrogen. So in practice, that narrows it down where you do it, but that's a much more viable, economically, it's much more viable because you make it where you need it, instead of using petrol to transport your hydrogen in a truck, which that's where you start losing point. So that's kind of interesting. There's a lot of them popping up in the world at the moment, and there's a lot of development in that area. So a good case study I found is what's happening in Europe, because countries are actually working together to make the hydrogen. So this picture kind of shows that different places, I think, where are we? In France, I'm French, so I keep putting that one. We're making hydrogen. Then we have a pipeline that's somewhere. This is way too tiny. I can't reuse this again. They have a pipeline in Germany to transport the hydrogen. And then somewhere else, we are storing it. Again, in Germany, we're storing it. And then we're using it that way. And then we ship it in Portugal to other places. So that's the idea of having all these places interacting with each other. On the scale of Australia, you have to imagine all the states working together. States in Australia don't really like to work together, so there'll be problems. But that's kind of the way to actually try to do this. And this is a close-up, I think, of a case. The text is completely unreadable, so believe me on that one. But the idea of this is that we have a wind farm. I think this is somewhere, it looks like the Netherlands. You have a wind farm and some energy coming from somewhere else. We split it into hydrogen, we use it right away, and we do this even on a small scale of how to use your hydrogen. So this is a bit clearer for the hydrogen pipeline. This is the one, I think, talking about how to transport your hydrogen across different places within Europe. For instance, if you have lots of wind farms near England and you want to get your hydrogen all the way to Portugal, well, you have to have pipelines to transport it across the ocean. And then you can store it in front with a massive aquifer near the border to Spain. So you keep storing it, then you transport it. It's the same. There's a lot of talks about having hydrogen made in Africa because they have a huge amount of sunlight and green and massive energy potential. And then ship it to Italy, and then it keeps going. In Poland, they have salt caverns. Well, let's use them for that. Hydrogen underground solutions in Finland. They're talking about massive hydrogen networks in Germany, so all of this working together. The big part of this is all a bit maybe it will happen. A problem we found with a lot of hydrogen projects is they don't always turn into a real thing, mostly because they're way more complex than people think. Typically, a hydrogen plant takes 5 years to make. 5 years is from the day when they sign the deal to actually having something. In 5 years, the government may change, the company may not exist anymore, or the investors may have pulled the money, and a lot of these projects don't actually happen. But what's important is that some happen and that they make a difference to build confidence that this can be done. So now looking at this for the UK, this is where, again, I go back to a pinch of salt. Found this chart was interesting is, how do you go from 5 gigawatt of hydrogen to 80 gigawatts? So you keep scaling up. What's interesting with this chart, they're not just scaling it up, they're using it for different purposes. So in this case, you have hydrogen production, I think hydrogen production over there by electrolysis, and then you start to store it in the UK because you make so much, you should store it, you make it offshore, not even in England, but having wind turbines outside. After that, by 2035, 2040, you've cleaned up all the harmful cause of hydrogen. Again, that may happen, and you can start to make more and more green hydrogen, and it constitutes 5–10% of the total hydrogen produced in England. And then now we can say, okay, by this time, they've fixed the power grid in England, so now you can all the power grid, all the gas grid can handle hydrogen. So that's a big work in 15 years. And then now we can say, okay, all the gas in England in 2040, 2050 is 100% green or 100% hydrogen. That's a gigantic amount of money to actually get there. But that's sort of one of the plans. And after that, you have over 40% of heavy mobility is powered by hydrogen, and we have hydrogen storage, make it ammonia, salt caverns, and we fixed a big solution. The problem of this is often, on these slides, at the very bottom, it has a logo of a company. That company may be a startup who has plans to become a multinational or multi-billion-dollar company in the next 20 years. So there is a journey, but that's the idea of it. Is it really about being? I think this is the UK Hydrogen Society something association. So again, it's people who believe in this who are going to make this slide. So now the question is, we've made all this hydrogen. What the hell is it even for? And a big problem we found recently that there is more enthusiasm about making hydrogen because there is a lot of money in that than there is enthusiasm for actually using it. So there start to be more demand of more supply than actual demand of hydrogen. And that's a problem as well, because then the company's tank can disappear overnight because the investors say, well, you're not going to use it for anything, you're just going to make a massive amount of it. And that's not helping anybody. So there's a big debate. So there's two most applications. So you can transport it and use it for something else. You make it into ammonia, very good for fertilizers, much cleaner than other ways to make it. Then there's the whole green steel part, and then there is the whole fuel cell part. So I'm working on fuel cells, so I'm mostly going to focus on that. But there are other applications of hydrogen in industry. So let's see. So hydrogen fuel cells. So this slide has a lot of different types of fuel cell technologies. I'm not going to go into every type, but I want you guys to focus mostly on the operating temperature and the efficiency of them. So to make fuels, the fuel cells have different amount of efficiency at different temperatures, and they require different catalysts. So low temperature PEM fuel cell, that's what's most established at the moment. They require platinum catalyst, extremely expensive. They work at low temperature, so not too much heat to actually operate them, but at the same time very expensive. Solid oxide fuel cells, you can use some fancier materials, but they work with much cheaper metals, but they need about 800 to 1000 degrees to even turn on the thing, to even get electricity out of them. And as you do this, the price, so as you lower the temperature, the materials are more and more expensive, and as you go the other way, you are more efficient. So the two that are really progressing in the market at the moment are low temperature PEM and solid oxide fuel cells. The one in the middle have kind of stagnated. They haven't really gotten anywhere beyond the lab, mostly because they're not that efficient and they're not that cheap either. So you have a trade-off of, well, no one is actually going to invest something that needs a lot of money and it doesn't give you that much power. And they have a lot of engineering problems. So next slide, I'm going to show you a comparison from an industrial perspective of, okay, I've got a low temperature PEM fuel cell or solid oxide fuel cell. If I'm a company and I just want to make electricity from hydrogen, how would I actually choose which fuel cell I want? Oh wait, no, that's not coming. That's coming after this. That's coming in a few more slides. So let's rewind for a second. Hydrogen fuel cells. I really need to check my slides before I come next year. So hydrogen fuel cell, they have been demonstrated in a lot of different devices. That's purely low temperature PEM fuel cell. High temperature fuel cells, they operate at 1000 degrees. You don't really want to have that in a car or on a plane because that thing is already taking so much energy to run them. But at the moment, on the stage of R&D, there is no actual challenge in putting a fuel cell into a device. You literally buy it off the internet from a fuel cell company, probably one in China that sells it for you for very cheap. You check if it's safe, you use it, and then you hire a bunch of engineers and you put it into anything. There is no more challenge in doing that. The main challenge is whether the application you've chosen is going to work. Is going to work as in, are people going to want it? So when I started my PhD, the company funding it made a really cool fuel cell phone charger. It looked about the size of a bottle. Half of it was a hydrogen canister, and half of it was a fuel cell. They sold zero, because no one wants to carry a gas tank in their pocket. The company argued, hey, everyone is using lighters, everyone smokes, that doesn't bother you. People were like, yeah, but that's an actual hydrogen cylinder that I'm supposed to carry in my backpack. It made all the talk shows, everyone in the world was like, it's awesome, the company hired people from Apple, and then they fired 75% of their staff. I was really lucky, I had finished my PhD 6 months before. The student who was doing her PhD after me nearly got fired, nearly failed her PhD because of it, because she ran out of money. But basically, point of this is where are actually fuel cells going to end up? So fuel cell cars excited people a lot in the last decade. I'm going to show you guys that they're probably never going to happen, small-scale fuel cell cars. Fuel cell diggers may have a potential. It's same for fuel cell trucks. When you need a lot of power, battery vehicles are not going to work because you won't be able to move your battery vehicle because it's too heavy. So unless you keep increasing the power to move it, but you increase the power, you need a bigger and bigger battery. The fuel cell motorbike, again, I'm not completely sure it will work. The prototype have been made, but no one actually used one. I think the project failed. Fuel cell trains, that got people really excited in Germany. The company pulled out, but the main argument was it's cheaper to replace a locomotive with a hydrogen locomotive than actually electrifying a power line. In practice, it may not necessarily be cheaper, but on paper and in theory, it sounds much cheaper to replace an engine than electrifying 500 kilometers of line. But still up for debate. One I find really interesting is massive fuel cell power plants. So literally having millions of fuel cells working together, and then you can power a city with it. But that also comes with its own challenges. So now let's see. So I've got a bit of a case study here. It's a rough example of how do you go from a fuel cell toy. So you can actually buy this online for $10 without any safety or anything. You can buy a tiny fuel cell, a tiny wind turbine of a toy of a company called Horizon, and you can make your hydrogen yourself. It's so small, it's completely safe. They don't even care about safety of it. And then you can make a tiny fuel cell, and this you can actually use to power a toy car. So how do you go from this, which generates pretty much less than a watt, to 113 kilowatt, or I think it's even higher now, 200 kilowatt fuel cell car. Where do you go from here to there? So first question is, what type of fuel cell do I want to use? After that is, what else is there? What is a fuel cell is probably the first question. Then what type to use? How do you make it larger and larger? How do you go from 1 watt to 113 kilowatt? Next question is, how do you put it actually into a car? And how does the car actually, is it going to work? So, and then the last part, that's what I'm talking at the very end, is how do you make them cheaper to the point that they have a market? So looking at this, so the point of this I want to show you is really that the technologies are so different that they end up with different application. So low temperature fuel cells, they operate around 80 degrees, so they make a lot of fuel cells generate water, so a lot of liquid water comes out. That comes with its own very problems. It requires very high purity hydrogen. It may freeze, so you need a lot of antifreeze. You can sort that, but it's still complicated. Solid oxide fuel cell, they have some advantages and some problems. The biggest advantage they have is you don't need to use 100% hydrogen. You can use hydrocarbons because you operate at such a high temperature. You don't need the gas as pure. You don't need to use platinum. You can use much cheaper materials. But instead of freezing, it requires heating to that temperature. So it can work really well in a factory when you've already generated the heat, but it's not going to work very well if you want to power your house and you need to consume electricity to turn on the fuel cell. That's the bigger problem, is how do you actually start it? And in general, I've seen less and less talks about it. I'm not sure they're going to happen. But the idea of this is it has potential, but it's not necessarily market ready. It's not ready for any market. So in terms of requirements from a company for any fuel cell, industry always wants the same thing. I want it very cheap and I want it now. And I want to be able to make a really big one out of it. So low cost, scalable, and also most importantly, you don't want to have to wait a day before you have electricity in your house. So you want it right away. So fuel cells are much more promising and much more mature, but in the very long run, and that may take a long time, high temperature may have other advantages. But again, whether they'll happen or not is still for debate. So from now on, I'm going to focus on PEM fuel cell because that's what I work on really. And that's what I think is more mature. So let's say you want to make a fuel. So imagine you're doing a PhD in chemistry. That's the case of my PhD student. They're making research purely on catalysts. So on the materials that go at the very inside of a fuel cell. What's the journey from here to there? So first you make a catalyst, then you scale them up to a device. That probably takes a couple of millions for research groups to actually do that, because it's much harder to scale up synthesis than it looks. It's not just, well, I'm going to hire 10 people and do it. You probably need equipment much more complex, and you may consume a lot of energy doing that. So your synthesis that you had really good in the small scale, you may find out that it's not actually green anymore because you're consuming so much nasty products that you may not want to do that. But let's assume you can do it. So you make it into a small scale, then you make it into a stack. A stack is basically a system that generates enough power. It's an assembly of single cells. And then you make it into a system, and then you try to commercialize it. It's on average 10 to 15 years between the start of a catalyst and the remote chance that it makes it into a device, or each and all the way. So how do hydrogen fuel cells work? Well, in principle, it's really simple. So you put hydrogen on one side, oxygen on the other side. Hydrogen splits into protons and electrons. The protons, give me a second, they'll come back. Where are they? They should go across. Yep, they go across the membrane. They go across the membrane. They react with electrons and water and oxygen, and they make water. So in theory, it's one of the simplest reactions there is. The first paper on fuel cell was from 1830, I think, when the guy said, oh, it's amazing, it's going to save the world. The next paper is from 1890, when the conclusion of it was, it's going to take a lot of work and it's not going to be easy to make this actually work. So there is a long journey, and right now the best catalyst for fuel cells are platinum. Platinum is one of the most expensive metal. That's a different problem for later in there. So now, okay, we've made a fuel cell, we got it. So low temperature fuel cell. That slide is a bit more technical, but it's the same concept. You have a cathode an anode when hydrogen splits in proton and electron, and the cathode when you have oxygen plus proton plus electron. It gives you water. And that's roughly how the structure looks like. That's just a cartoon of it. But the main giveaway from that is there's a lot of gas diffusion and water management challenges in fuel cell. It's not quite as simple as the first slide. You have a lot of different problems. Fuel cells are basically an mechanical engineering nightmare, or dream, depends on who you ask, because you have thermodynamics, two-phase flow, chemistry, and at the same time different current density in different areas. and then you want to make your own materials. So in a very, very compact system, there's a lot of different problems. So there's basically a job for everybody, but the problem is you want these people to work together to make something that works. So I've made a cartoon once about how to make it. So typically the way fuel cells start is some carbon fibers, so very, very cheap, carbon paper, and then it's coated with something, make it more hydrophobic. And then we've add more carbon to increase the contact area, I think, make it with carbon nanoparticle. On top of that, we put some catalyst, so that's the material in yellow. Then we put a membrane in the middle to exchange protons, and that's how your structure looks like. So it's actually fairly simple. Most of it is done in industry. The catalyst that someone makes, you make them, you deposit them directly. It's fairly straightforward. That's actually how it looks like. So fuel cell itself is a membrane, is a material of about 1 millimeter thick with all of this stacked in it. And so this one's pretty tiny. You have a thin membrane, some catalyst, some materials, and to make it the potential out of a fuel cell is 1 volt. So one way to make a high power is you make it massive, and then you can draw a massive current from it. The problem of that is because they have complex thermodynamics, there is a maximum size a fuel cell can be. Probably above 100 centimeters square, you start to make so much water in one location that to transport it from the inlet to the exhaust, you have flooding issues, and it actually stops to work. So instead of that, so as I said, probably 100, 200, 300 is the maximum you can start to make. So now you're stuck with something of about 10 by 10 or 15 by 15 centimeters square. How do you actually power a car with a 1 millimeter cell? So best way, so this has been done in industry forever. You just stack them, you put them in series. Instead of having 1 volt, you put 10, you have 10 volt. You put 100, you have 100 volt in that kind of range. So it's called very much a stack. And you just keep increasing it to increase the voltage and power. So I did that math a while ago. Well, I was doing fuel cells for, I think, for a phone charger. I actually made one in the lab to power a phone. And then I made that, and I was so excited. And then we were like, that's not actually very exciting, because everyone has done it before. But you can actually you need 5 watts to power your phone. The source is my phone at home. I checked that. And so for that, typically you probably want 12 volt, a very, very tiny current, so it's safe, so you don't blow yourself up at home. That's 0.04 amp on a 10 centimeter square area. And then, so you make a few fuel cells, same thing, 20 cells, so you stack 20, you make them pretty tiny, you're good. And then I've looked online for the Toyota Mirai specs, and you can very easily reverse engineer and get roughly the idea of the size of it and how many cells. So 113 kilowatt, assuming they work at the same kind of operating point, then you need in the 370 to 400 cells. So 400 of these in a stack. It looks probably this size, it's still quite compact, and it will give you 220 volt and somewhere in the 20 to 50 amp. So that's per cell, so that's quite a lot of current going through these. But looking at this, now we're like, okay, we've made a stack, we understand that, how do we put it in a system? So on the left side, you've got the fuel cell toy car, and so for that, you basically need nothing. You just have your fuel cell electricity, and it powers a tiny DC motor, and that's a fuel cell toy car. That's the one you can buy off the internet for $20. Now you've got the much more complex one, which is the real one that's coming from Toyota. The bigger they get, the more complex the water and heat management becomes, and you need a lot of different parts. So the first part you need is fuel cells use air from the atmosphere, but there's a lot of impurities in the air from the atmospheres, and you want very clean air going fuel cells, so you need some sort of filters. What else do we need? You want to compress your air to a certain pressure. You need a converter. You produce water from the fuel cell, but you want to be able to recycle the gas that are coming out, so we probably have a separator. And then it gets bigger and bigger. I'm not entirely sure what the air-con converter is in the picture, but you have a lot of different components that come in. And that's the part that becomes trickier and trickier is, well, the only power source is the fuel cell. So how much power am I going to consume to be able to turn on the fuel cell? At the moment, that's where there's a lot of work on this area, is 20% of the power that you make from the fuel cell is used to actually turn it on. So there is quite a problem, and typically the way fuel cells work is there is a battery that powers the actual system. The fuel cell recharges the battery, and to start the fuel cell, you draw power from the battery, and eventually you make enough power that you can consume the power from the fuel cell to operate it. So there's still quite a lot of fun problems in there. So how do you power a car with a fuel cell? It's the same for a truck, a plane, a boat. It's all the same concept. It's mostly fuel cells like working really well at a fixed power. Cars and all of these like to change the power so you can actually speed up on the highway. And you can't do that if you just run a flat power. So the way they work is mostly the fuel cell is actually a hybrid system. It's recharging a battery. All the power fluctuations are taken from the battery. The fuel cell keeps recharging at a set power, or may change a little bit, but mostly stable. The fuel cell can't remotely cope with power fluctuations, because you start to make water. If you generate a lot more power suddenly, then you're making tons more water that may need a whole new, that may increase the whole challenges. So battery for basically everything in the actually running, and the fuel cell is constantly charging your battery. And there's been, I think, one fuel cell car doing a demo Sydney to Melbourne on one full tank of hydrogen. That was done by a professional driver that didn't even stop and knew what they were doing. I reckon if I was to do it, it probably wouldn't work, but they managed to do it, which showed the concept that you can do a very decent distance with a hydrogen fuel cell car. The interesting thing, and this is where this talk gets a bit darker and not as optimistic as before, is this was the prediction on the left side from 2017 to 2024. I'm showing this slide next week in Imperial College in London. I'm going to give talks, and this is where we were hoping it would get. So 2017, we've made a 10,000 fuel cell. By 2024, we've sold 250,000 hydrogen fuel cell cars. In practice, that hasn't really happened. If you look on the left side, so BEV is battery fuel electric vehicle, like Tesla, and FCEV is fuel cell electric vehicles. And well, battery vehicle took off, went to already were close to 1 million, and now they're 10 million a year. Fuel cells, electric vehicle, passenger vehicle, actually went worse in the last 3 years. And that's a really interesting case of, did we get this right, or did we focus on the wrong market for fuel cells? And these numbers get harder to find because fuel cells companies don't really want to highlight that they're not doing well. But a lot of projects that were on passenger vehicles for fuel cells, the companies are slowly withdrawing the investment because people figured out, well, actually, I can drive with a Tesla pretty far. Maybe the whole rhetoric for fuel cell cars, well, you may not find a power station in the middle of nowhere. The answer of people was, yes, you may. So they may still have a place, but for passenger vehicles, I'm less and less sure they will happen. Also, I think at some point in Japan, which was during a massive bet of hydrogen fuel cell, all the hydrogen refueling stations tripped at the same time. So no one could refuel their fuel cell because they were relying on one company to make the hydrogen. So that had a massive impact on people mentality going, I'm not sure I want to buy a fuel cell car if I won't be able to use it anymore. So that gave you some problems, but the interesting part is fuel cells, even if this has taken a massive hit, fuel cells haven't actually stopped. And this slide, if it actually works, oh yeah, there you go. That's the main reason to me why fuel cells absolutely have a place, is the bigger the system, the longer it takes to recharge your battery. So looking at fuel cell buses, this is obviously coming from a company who is selling hydrogen fuel cell buses. So you have, again, take it to a pinch of salt. But in the time it took you to recharge how many, 20 or 20, I don't even know how far this goes, 22, 23, 24, 25, you've only recharged one battery-powered bus. The other big problem you've got with this, obviously batteries are getting better and better, but the other problem you have with this is if you want to recharge a fleet of buses with electricity, it may take the same amount of power than the small town next door. And as well, you typically want to do this when the buses are not running at night. That's when you want electricity when you go home. So that's where the whole debate comes in, is basically when you want to have high power, high autonomy, and you want to be lightweight, batteries are not quite going to work. They may keep improving, but the fundamental point is to have more power from a battery, you just have to make them bigger and bigger and bigger. There is not much of a way around it. Whereas fuel cells, we don't have that problem. We store more hydrogen. We find clever ways. The fuel cell remains the same size, but we can have a different pressurized hydrogen cylinder, different technology, and we can store in more and more gas. And the weight doesn't change because it's just the cylinder at different pressures. So the two markets that are looking kind of more exciting at the moment is trucks and heavy-duty vehicles. I put them kind of as one. Trains we'll have to see, and aviation is one that actually has people betting a massive amount on fuel cells. So let's see where we are. So again, go back to the internet, same kind of source. This is the plan for hydrogen fuel cell trucks. So 2024, we had 5 million, million or billions or 5, whatever. And by 2034, we've increased by about 20 to 40 times. So that's, again, exciting. Whether it's going to happen or not, you'd be my guess. But because this comes from a hydrogen, from a company who is just about raising money and wants you to invest, it may not quite go as far as that. But the idea is there is potential for technology. So why would you actually want to bother with a hydrogen fuel cell truck if you can have a battery-powered truck? Well, the main reason is the battery-powered truck becomes heavier and heavier. When you want to carry things with the truck, you kind of want to have the chassis as light as possible, and that way you can transport more goods. With a battery-powered truck, 30% of your payload is just moving the truck. So you lose a lot of energy that way. That's why it's not as good. And again, as I said, the fuel cell recharges a much smaller battery. So you save a lot of weight. And the good thing with trucks as well is people were anxious saying, well, I'm not sure I'm going to be able to recharge my battery where I want. Well, trucks, people know exactly where they're going. You know which way you go. Go ahead. You know where you're going, you know exactly your route, you know your drivers, you know your fleet, so you can actually plan the stops very well. And you have all your trucks powered, you have all your trucks stopped with the hydrogen option. That's more feasible, potentially. So how does it look like? So the cool thing with fuel cells is the whole system in every single size is actually exactly the same. So in that case, they're storing a massive amount of hydrogen cylinders on the back of the driver. The driver may have something or two to go about this, but at this stage, I don't think companies have started to ask drivers if they minded having 10 tanks of gas behind them, but one day they may argue, but for now, let's not care about it. And then you have your fuel cell module and your battery system, and that's how it looks like. There's a lot of talks about it. It's exciting people a lot. Whether or not it will happen is still up for debate, but conceptually, it has a commercial sense. Now, there is a fun one, that's what I'm actually working on at the moment, is hydrogen fuel cells for planes. So why do you want to bother with fuel cells with hydrogen plane? Well, the first reason is we are all living in Australia here. The only way to leave the country is take a plane. And Australia is one of the biggest emission of CO2 per capita, I think, because of aviation. And in the world, I think aviation is 3% of the CO2 emissions. In Australia, it's closer to 5 to 6%, simply because there is no way to get anything out of Australia without taking a plane. Unless you take a boat to New Zealand, that's already taking a lot of power. So battery power plane, and I tried to dig up a photo later, require a completely new design of the plane. The drawings I found, I couldn't find them today, but I found them a few years ago, is imagining a wing that's 10 times bigger and all the batteries are in the wing. The problem of that is right away the wings become much heavier and you struggle to actually move your plane again. There's a lot of companies who are actually doing this in Australia and in the world. There's Boeing, Airbus, and I think one of the companies, ZeroAvia, who are doing this large scale. And there's also a fun little company, two fun companies in Sydney, in Australia, who are doing a very, very small scale, trying to prove the technology. But the problem of this is it's still actually not that simple to do. So again, look at the market size. I think, again, this is billions of dollars or millions or whatever. There is a potential. It's not as exciting people yet as fuel cell trucks. We're only from 1 to 28. The fuel cell trucks were 1 to 150. The reason for that is this is way more R&D, and the technology is not there at all. There hasn't been a large-scale hydrogen fuel cell plane just yet. So again, let's just see what happens. So I'm going to go a bit faster into this slide, but basically a big problem of hydrogen fuel cells for plane is the weight of the fuel cell. So planes like solutions that are very, very lightweight. Fuel cells generate liquid water, so they're around at 80 degrees. That means that you literally need to store your water, and you also want to cool them to 80 degrees, so you need to have a whole water recirculation system. That consumes a lot of energy. It's heavy. You just don't, for long-term fuel cells plane, you probably don't want that. There's high-temperature fuel cell that are an entire kind of worms. My PhD student is having gray hair every day with high-temperature fuel cell because they're much more complex to operate. But the good thing of them is they don't need liquid water, and they don't generate any liquid water. So they're running at 160 degrees, which open its own challenges. It needs different membrane, different electrolyte, different everything. But the idea is, even if you're winning on one side, you're losing because the technology is not quite ready yet to work. But they have great potentials, and companies are looking low temperature plane first, and eventually high temperature fuel cell planes. Again, only 160 degrees, still feasible. So this is where they put my face everywhere this year, because I'm doing a tiny project on putting a high temperature fuel cell on the drone. We drove the drone yesterday. We drove it straight into a tree, so that was a good step. At least now we know the drone flies. It took us 4 months to be confident to fly the drone. Then I also learned that UNSW is a no-flight zone. So you're not allowed to fly drones in UNSW. And also it's more than 5 kilos, so I'm not even allowed to touch it myself. So we found there is a guy called the chief remote officer in UNSW. I just thought he worked remote. No, his whole job is to check drones. So he flew the drone with me and his friend flew it into a tree. But anyway, bottom line of this is that's what we're trying to do. The reason we're doing it, it may not actually make sense for drones because it's still, you want the fuel cell to be around 150 degrees. But the point of it is to show how we can do it and to solve the problems that a larger scale company is going to face as well. So that's what I'm doing at the moment. So we're scaling up our catalyst from about a tiny vial to a slightly bigger vial, a couple of grams. That already requires a full-time master's student. Designing and prototyping the fuel cell stack, that took me a day because I know how to make them. Prototyping it is much harder. I've got a company in Deakin who can make them. I'm not sure they can deliver. Otherwise, I'm going to make it in China because they know how to make it and it will be very, very cheap. And they don't care about making it in the best way. They'll just make it the way I want. And then we've got putting into the drone. So that's a lot of hardware electronics to figure out, but that's again, fairly easy from an engineering background, as in there is no challenge to solve. It's just hardware integration. And then we're trying to solve this. And one of the fun problems with this is the biggest problem we had is we need to heat up the fuel cell to 160 to start it. So I learned the company somewhere in Australia who's doing it for a plane, and I asked them in the webinar, how are you going to heat up the fuel cell? They answered, well, we have a 450 kilowatt heater on the tarmac. So that may be a problem long term. I'm meeting with them at the end of the month to see. But I think there is a problem of where is the energy coming from to start your system. That's what I was saying before. Even if you win, you may still lose on the other side. So the big problem of aviation, and that's why fuel cell, apart from saying, hey, they're cool, I want to make them into a plane, the big problem of flight is that, you guys probably may know this more than me, is that it takes more power to take off than actually fly. So to move the thing off the ground. And the problem of that is that you need more power. So if you have a battery, you need a massive battery that you would use to take off. And then to fly, you need less power. So that gives you a full funny problem of, well, I've overspec'd my system, and I didn't need to, but there was no way to start to get moving otherwise. So with the fuel cell, that's slightly less of a problem. You may find a way to operate them at different pressures, but it's still a problem. But overall, you get a much lighter battery. The battery may take some of the takeoff power, and then when you get flying, the fuel cell takes all the rest. I think there's been fuel cell drones before. They managed to go from, I think, 30 to 45 minutes to 5 to 7 hours. So there is a big market for that, even for small scale. And the reason I'm making my life much harder for high temperature fuel cell is because they don't need any liquid cooling. So again, potentially they're much lighter. So how hydrogen fuel cell will look like? That's what I was trying to say before. So you basically put all your hydrogen in the wing. The way right now you put the fuel in the wing. The fuel cell is powering the engine. You take your oxygen just from the air by moving, and you get water vapor. A battery plane, that's the one over there. You can see there's something weird at the bottom. The bottom part is literally the battery. That's an artist's view of it, but you basically need a massive battery, massively heavy battery underneath. So now there's a fun company based in Bangtown. This is real. This is an artist's view, but I've seen the real thing. They're making a giant drone big enough that you can go inside of it, and they're calling it a flying car. And I thought they were insane. Then I saw the guy, and I was like, yep, you're definitely insane, but you've been given enough money to do it. So they're actually trying to do this for real in Bankstown. And the plan for that is for accessing remote areas within Australia. I thought they just wanted to be in downtown Sydney. They told me that that wasn't going to happen. Anyway, so the point of it is there is all sorts of scale for fuel cell planes. I reckon projects like this are potentially more of a learning for massive companies. For instance, Airbus, if they try to do something right away on a massive scale, that's not going to work. So they're going slowly from like a 5-people passenger plane to 20 people, and then slowly learning and getting there. That's why this is not going to happen overnight. That's why right now the market to 2034 is much lower, because it's going to take an enormous amount of R&D. But potentially really interesting. So something I've actually just made this morning as well is, well, can we actually just use hydrogen directly? Do we actually need to bother with fuel cells? So you can actually put hydrogen directly into an engine. Let's see if that plays. Yeah, there you go. That looks very fancy. I think it's from a company making hydrogen engines. You inject a tiny bit of hydrogen right there. You burn it into an engine, and then you power your engine that way. So on one side, it's much better than fuel engines. On the other side, you're still not quite clean, because when you burn hydrogen at high temperature and you combust it in oxygen and in air, you actually end up cracking the oxygen and the nitrogen. So you make water, but you also make nitrous oxide. So the combustion engine people said, hey, yeah, but I don't make CO2 anymore. That is true, but you make nitrous oxide, which is a very dangerous greenhouse emission, which is the most potent greenhouse gas. So there is a way to go. There is talks that you can clean it, but it's still, to me, it's not a long-term solution. Yeah, I see it almost more as the oil and gas industry trying to stay in business by saying, hey, I can just put my hydrogen into this and it's cheaper. In practice, and this is just my views of it, in practice, it may not actually really happen and it may not take off, but it's seriously considered because it's much easier to do. You don't need to change the engine, you just need to put a hydrogen tank and modify your engine a little bit to inject hydrogen. I've seen one yesterday. It's literally they drill a hole near the engine and they inject hydrogen instead of gasoline. So that's potentially promising, but it's not quite clean. Sorry, that's playing in. Could we make hydrogen combustion engine cleaner? So as researchers, we try to do everything and anything. This guy, I think they're making some sort of, vanadium oxide, tungsten oxide, titanium oxide catalyst. That's probably some sort of nitrous oxide scrubber. And then they make out of it, I haven't even checked completely, but they make some products. The problem of that is that means that your car is going to be generating something that you'll have to get rid of eventually. So while it's promising, and it's a good idea to try to work towards that, you need to think of the real case of how is my car going to release that product? Where is that going to go? Am I going to have to change my catalyst every 6 months, every year? What scale? Does it make sense? So it's good to remain agnostic, but this is not going to have clean hydrogen combustion engines. I don't think will happen anytime soon. They may be cleaner than regular engines, but they're not as clean as a hydrogen fuel cell. Another fun thing of hydrogen engines is because you're not burning fuel, you're burning something which is not as efficient, so you also make less power. So the biggest advantage compared to fuel cells to lock on hydrogen combustion engines is you don't need to make a new device. You just modify something that exists. From a perspective of an industry, it may make a lot more sense because a plane that is made today has a lifetime of 20 to 30 years. If you need to tell a plane company that made their plane 10 years ago that they need to throw away their plane, they're not going to want. It's going to cost so much money, it's not going to happen. So this could be looked at a short-term solution, and when the plane expires, then it's replaced by a much, much greener plane. But we need solutions not just to go, hey, in 30 years we'll have decarbonized, but we need solutions that actually work now. And this may work for now. It may be a bit like putting a bandage on a bleeding wound, but it's better than bleeding out. So that may be a solution. I'm still mixed on this, but I see it as it may help us to bring net zero, to, for right now, decarbonize by putting hydrogen into a device that already exists, instead of launching a new industry. And while this happens, we can develop the new industry, but we have 20, 30 years to do it. And so that's the trade-off of how do you actually get there. So there's plenty of work on that, but again, you need a million mile is the truck. There is a program in the US called the Million Mile Hydrogen Fuel Cell. I don't think they've ever run a fuel cell for a million miles so far, because it will take way too long, way too much, like 2 decades, but this is kind of the idea of this. So now I'm going to give you I think I'm going to finish in the next 10, 15 minutes. I'm going to give you an overview about the kind of research I do on fuel cells and just give you a sense of it. So the biggest problem for me for fuel cells is that too expensive. That's what I've been telling you guys so far. They cost so much money that it doesn't make sense to make them. So what do we have? From a fundamental perspective, fuel cells using platinum. The price of platinum is somewhere it was $100,000 per kilogram at some point in the 2010. Now it's going up and down. But basically the price of platinum is following the world economy. That's how, and these days, most of platinum comes from Russia. So we're going to have problems, we already have problems with platinum. But the good thing is, well, we can replace it by something much cheaper. So what do we have that's way cheaper? Iron actually doesn't work too badly for fuel cells. So we can replace it, that's much better. And iron is pretty much unlimited. It's almost free. We're talking 1 million times cheaper, but it has a lot of problems. It's not as simple as I'm going to take a bottle, change water containers. It's a whole new industry to actually even do that. So let's see. That's my research talk. So I've got things like this to keep people in the conference awake. Most of the time it doesn't work. Most people don't actually look at the slides. But the idea of this is we want to replace platinum with something else. It may work really well at low in a very ideal lab scale condition. The moment within a fuel cell, the new catalysts have a tendency to die out in about 60 hours. Something that a PhD student made in a year of research, in the next 60 hours, the performance have dropped to 0. So a lot of problem in that area. And we do a lot of tests. So this is basically moving from a liquid environment in a chemistry lab in a little beaker to an actual fuel cell, which is completely solid. So a lot more complex system. And the way the reactions happen is called the triple phase boundary between the active sites and the transport of protons and electrons. So this may look quite simple, but in practice, it's really complex to build a fuel cell that has enough triple phase boundary. If you don't have enough triple phase boundary, you may have a lot of catalyst, but a lot of it won't actually do anything for the reaction because it can't actually react properly. It will just sit there and no reaction happening. So now let's see. So without bombarding you with too much details, the problem of platinum-free catalyst is they're not as active as platinum. So to match the performance, what you typically do is you put a ton of catalyst. By a ton, I mean instead of putting, 0.2 to 0.4 milligram, you end up putting 1 to 6 grams. So it's a catalyst layer, instead of being in the 10 microns, so very easy to transport protons, electrons, diffuse gas, is closer to 100 to 180 microns. That's the thickness of a human hair. In electrochemistry, when you start to see stuff with your own eye, it's not a good thing because you need to conduct electricity through something that's thick enough that you can see it. So a lot of problems come from there, long pathway, and the kind of work I've done a lot, what's really fun is we know it's a problem, but how do you monitor the problem? How do you quantify the problem? So I've done a lot of fun papers in that area. But overall, as an idea, this is the kind of performance gap you get between different materials. So platinum-free catalyst gets you somewhere around 1 watt. A commercial, this is a lab fuel cells, get you 1.8 watts per meter square. And a commercial one probably gets you to 2.5 to 3 watts per meter square. A lot of papers, the way they cheat is they operate the platinum fuel cells badly on purpose. And that way they say, hey, my catalyst is very close to the platinum-based. That's because they haven't operated the fuel cell well enough. But the reviewers don't always know that, so they can claim, I've bridged the gap with platinum. But a company would say, hey, my fuel cell, the same catalyst will do much higher. So there is a debate of how do you bridge that gap, but the idea is making better catalysts and figuring out what's the problem. So the bigger problem of that is not even the power. The power is getting up. I think people have reached 1.8 to 2.5 to 2 watt. I don't think they've reached 2, but I'm sure they will reach 2 very soon. The problem of them is in 30 to 80 hours, in 100 hours, most catalysts have lost 30 to 80% performance. They have been breakthrough, really exciting recently, but most of the field catalysts, they just don't work for long enough. So what happens is you publish a paper in Nature, in Science, and the last figure on the very, very last sentence, you conclude stability issues haven't been solved. And you dig up the figure, and the thing is that has no more power in 20 hours. They have managed to publish in Nature with stuff like that, because people are focusing so much on the exciting design of the material that they don't care if it actually works or not on long term. So it's really tricky to figure out. So I've got a graph like this, I think. But the idea of this graph, what you've got over there on the very top is how stable they were. So these materials, they gave you a certain power between 0.4 and 1.4 watts per meter square. And in 35 hours, you lost 80% of the power. So nothing is literally, it's not just the power is gone, but you can't actually get it back because the materials have fundamentally degraded. It's just degrading at an extremely fast rate. And the funny thing with that, and I saw that share that one, is it degrades so fast in the first few minutes of operations that you can't actually get the power that you've reported twice. You report it, so you probably hire 5 PhD students, you do the experiment 20 times, you report the best, but what you don't show is the moment the student repeated it, and that may be captured in 5 seconds. That's what happened, then I ran it again. That's what happened the third time. When I show this in conference, I often have a few people who are doing this, because everyone knows that, but we don't like reporting it officially. So the big problem is, how can you even claim that you had 1.4 watt if you try to run it twice and you only reported 1.2 watt the second time? And the third time you run it, and it's literally in 5 minutes, you've lost 10% power. So a big debate of are they even reliable, and it's quite hard to actually analyze them. So To go a bit more into the details, they have two problems. One problem is they use iron, and iron leaches out, so physically gone. The other problem is they have carbon corrosion. They use carbon-based material, and around 80 degrees in acid, carbon has a very strong tendency to corrode. So what happens is, well, the carbon corrodes, so you had your nice structure, and eventually you have so much corrosion that your catalyst site over there is also going to fall off. And then you end up with just carbon that doesn't do anything for you. So that happens a lot. Quantifying it is what I've spent a bit of time doing. To go a little bit into it, what I've done is, here's the catalyst we've made. According to the field, they were actually fairly intermediate stability materials, given that in 60 hours we lost, I think, over 50% of performance. People said that it was actually okay. That was the scary part. Is that literature that we looked at literature like, oh, that's actually not too bad for the time. So we tried to replicate it, but instead we tried to make loads of measurements in between. And what we figured out, and we got really excited, and that got us plenty of papers, is that the phenomena happen at different times. So iron leaching happens at the very beginning. Carbon corrosion happens much later. This slide should move. Oh yeah, there you go. And the important thing of this is we're only able to do this with loads of electrochemical measurements. A lot of people in papers, they just report a stability graph with no data, with no explanation, and they just conclude, I'm going to quote the paper from 20 years ago and tell you that's why it's degrading. But papers now are changing to actually trying to understand what's happening. So some stuff we've done showing that in London. So you guys, the first trial, it may go horribly wrong this station. But overall, the big problem of the catalyst is they make hydrogen peroxide. Hydrogen peroxide is a poison and destroys the fuel cell. So we want to avoid making hydrogen peroxide. The reason we make hydrogen peroxide is we absorb oxygen. The oxygen is absorbed way too much. So instead, we try making dual metal catalyst, where we kind of share the load across two metals. So the absorption energy is not as high. That kind of works better. The funny thing for us is we probably tried the wrong metal, but that gave us an interesting study because the material was just slightly more stable, but enough that we could see the difference between the two materials. So that's what we did on this side. We did an iron manganese nitrogen carbon and an iron nitrogen carbon. And instead of making 2% hydrogen peroxide, we make 1%. And the two stability were different enough that we're like, okay, we can do a study. It will never get to nature because we don't have something stable, but we have something more stable and we can figure out why it's more stable. And the good thing with these studies is the next PhD student in the group, he knows now, so he can fix it. That's what they're doing right now. The guy has graduated, and he was really upset for years because he didn't fix the stability problem, but the next guys who are working right now, they're actually improving it. You need to be able to figure what the problem is before you fix it. And so we did some measurements like this, and the kind of thing they show on the left side, oh yeah, that we don't have as much carbon. So the HQ is carbon corrosion. So with any carbon catalyst, there is a massive amount of corrosion. And with this catalyst, there's not as much. Also, the iron peak means we're losing iron, basically. It's getting bigger, but it's not quite for the right reason. It's getting bigger because we're corroding it so much. There is more active sites available, but eventually they're not the ones we want. On the left side, that doesn't change as much. So we've kind of sort of fixed we haven't fixed the problem, but we can understand, okay, this catalyst is kind of better, and we can exactly quantify why it's happening. So now actually moving to another part, I'm sorry, there should be a Y here. There you go. Need to fix that for London on Sunday, on Tuesday. So water accumulation and flooding makes the fuel cell less efficient. So what's happening when you have flooding in a fuel cell? So you literally produce water. If you can't remove it, it will just accumulate in the same place. So that means it's flooding, and you can't actually remove it anymore. That may look straightforward to do. A lot of people in chemistry say, hey, it's an engineering problem, it's easy. It's not. It's really, really not. It requires often to redesign the entire fuel cell to have less flooding. And that's not necessarily straightforward. So I've got this slide here. This is to give you a sense of, that's rough. That's not the right scale in terms of accuracy, but it's roughly what happens in a small scale, in a fuel cell. So every single point produces water. And we have flow fields, flow channel, where water just flows through because we are pushing air through. And we have the ribs. The ribs is area when you have electrical contact. The water can't actually go away from underneath these areas. That gives you a lot of fun problems if water builds up really fast. If water is not removed, it blocks access to the catalyst. And so the solution for this that we worked on is, well, maybe we can't fix it, but we can do a lot of simulations to figure out exactly what's the problem. So the first part of this, and then there's a lot of pretty pictures coming up on this, is when you do some imaging, if you guys have done any SEM or at some point, you want to zoom in to get a nice picture of a clean area. But the problem you've got is whether this very tiny area represents a larger area. And looking at a fuel cell structure, it's not actually even this is only on the 200 micron scale. Nothing is actually very uniform. It varies really fast. And problem of simulations is often we want to go, okay, we're going to simplify everything. Just say, hey, my porosity is 80% and my tortuosity or permeability is this much. But in practice, it may be massively heterogeneous. So one case is just simplify everything, or just take a tiny volume, scan it with X-ray imaging or something to get the structure, and just assume my tiny area represents the much larger area. And we tried to work around that, and we had to use a lot of AI for that. So this should play. So just to give you an idea, this image is actually X-ray imaging. Like imagining you're at the doctor and you have different slices of your MRI. These images are different slices inside the fuel cell. So we're just moving through the fuel cell. And what we did, I say we, I mean people way smarter than me did this with me, when I just directed them and they made an amazing piece of work, is that's the Ying over there. You start with an X-ray image, not a very high resolution. Then we used AI enhancement, and we get to this image, which is much higher quality. And then we segment it using, again, more AI. Segmentation is to identify what each material are. And on the gray image, you can't actually do any simulations. Once you've segmented it, you can convert it into a STL file or a drawing, a format, and you can run simulations on that. So that's what we did over there. We got to this kind of images. I've watched this way too many times because the first time I got something in Nature Index journals. And then we looked at it, well, okay, what can we do with this? We've got something cool. So we can actually do simulations of water and gas transport in fuel cells. So that took a humongous amount of computing power. It looks like nothing. To run this was on the fifth most powerful computer in the world, or actually I think the most powerful computer accessible to civilians, which then they run it to simulate two-phase flow dynamics. That was accessible for us through a grant. And the idea of this is, while we're producing water, it's emerging out of a porous media, and it's quite complex to remove it, and this is kind of where water is moving. So the fun thing of this is it really shows a lot of information about how water is transported, and we can also, I'm trying to put it in the right frame, you can see how changing regimes changes the water management, the water transport properties completely. And the way I'm working on, that's what I'm working on at the moment, is now I've got a cool model that I can use, but this is we used a real structure, but we overlaid a fake flow field, so fake channels. We just went, okay, I'm going to put channels that look like this and just see what happens. What I can do now is we can try to be cleverer, change the design, do the simulations, then access some really fancy prototyping equipment. Like we upgraded our CNC in the lab to be able to make something in the hundreds of micron scale. So we make it, and then we say, okay, the simulation says it works, and we can put it in the lab, and oh, maybe it will work. Maybe it doesn't, but we can actually close the loop between simulation and experiments. And that gives us some really interesting work that we're doing right now. It's been a year that we have tried to get it published, and maybe it will get published soon. But the idea of this is do simulations for a purpose. A lot of people run simulations because they're just interested in the problem, but they don't actually fix the problem. They just run simulations for the sake to get closer to resolving it. So instead of here, what I'm trying to do is resolving the problems. So now, this is pretty much, you guys are pretty much free after this. So hydrogen fuel cells, they're a complex device. They're very much a scientist's dream and an engineer absolute nightmare. This applies the same way. I haven't focused on that to making hydrogen. It's the opposite challenges of a fuel cell. Instead of making water in gas, you're actually making gas bubbles in liquid. So all the problems switch, and the problem you want is how do you remove the bubbles as fast as possible? If the bubbles stay inside the actualizer stops working because you just have something packed with gas, and liquid can't actually make hydrogen anymore. So same problem. And the biggest problem in terms of transportation is it's nowadays very easy to make a fuel cell anything. 10 years ago, there was a lot of challenges. Now we know exactly how to do it. The problem is, where is there a market for it? And it's still, aviation seems to excite people right now. In 10 years, they may say, no, it wasn't aviation all along, we wanted something else. So we'll have to see. And it's really about seeing it for the long-term solutions of, I believe it will happen, but it may keep changing, the field keeps changing, so you have to stay up to date with what's happening. And that's about it for today. So thank you very much for listening. And if you guys have any questions, we've got as much time as you want. You can ask any question you want.
Thank you so much. Let's just
Thank you.
Yeah.
Yeah.
Such an amazing presentation, Quentin. In fact, actually, you cut through the hype of the hydrogen.
Yeah.
And I really like the terminology when you said the hydrogen evangelist.
Yeah. Yeah.
It was an interesting-
I've seen them on LinkedIn. It's amazing. The titles make no sense at all.
You know what? Honestly, like I was reminded by myself when I first, I think it was a couple of years ago, and my research focus is more on heavy vehicles, port logistics, heavy basically transport vehicles. And electrification is such a struggle for those use cases. And I remember that when I first actually kind of was exposed to hydrogen fuel cells, I thought, that's the solution. That's the solution. I gave a presentation. I'm so embarrassed. Actually, I cut it off, hid everything.
Yeah.
Because you just get excited.
Yeah.
And
And then it doesn't necessarily happen.
but I really like that you presented all of the realities around hydrogen. And that's what actually we have to learn in university, because you will be the future environmental engineers. You will be the future decision makers in government. You will be the future advisors. And you will be the new generation that, the new generation of engineers that could basically
Fix this.
fix this problem.
Like,
But
we
again,
are too old. We've shipped out for the next 30 years. We're gone already. Us to fix the problem.
Absolutely.
Yeah.
So, but then again, the resilience
Yeah.
of the hydrogen researchers. I'm also kind of very appreciative that we shouldn't give up.
No.
So that's why the science and engineering is. So despite all the challenges, we shouldn't really give up. And there's no competition between
Batteries.
energies,
It's
or
all.
there's no competition between battery or hydrogen.
They just need to work together.
Exactly. So they could be complementary. So that's always my
Mhm.
point
Yeah.
also when someone asks me in a conference or over barbecue or whatever, okay, so do you reckon that hydrogen will win this race or battery? I said, there's no race.
Yeah.
I don't see any race. But again, that research and development. So we have to still continue. Biodiesel could be some solutions.
Hydrogen engine
ammonia.
is whatever is cleaner than what we've got is better than what we've got right now.
Exactly. So the bottom line is we have to decarbonize.
Yeah.
We have to do it quick. Otherwise, we will.
Other guys, you guys, your kids are screwed. We'll be dead by then, but your kids are screwed. In simple terms.
Yeah. So questions.
There's no stupid question. Go for it. The worst question I've ever heard is one guy asked me, "Why do you put electricity in this piece of metal? It's done nothing wrong to you." So you can ask this. Yeah. That was legit in a conference.
We have a luxury of having a small group at the second half. So we're going to actually just be very casual.
Yeah.
So don't be shy.
Yeah.
Anything that comes to your mind. Okay, no pressure.
No
then.
pressure.
No
Cool.
pressure.
You're most welcome. My email is somewhere in there. You're most welcome to email if you have questions and you are shy. That's fine. Once someone did it. Yeah.
Yeah.
I guess it feels like, it's not really a question, but it's more like if money is a big issue with not progressing as much
Yeah.
as we have, and because you were saying like there's been projects with hydrogen fuel cell, like even the
Yeah, yeah.
valleys,
Yeah.
and nothing happening with it is because investors pull out.
Mm-hmm.
So I guess it feels like there's more of a future if there's more of a commitment
Yes.
from big investors.
Yeah. So the big progress has been with the hydrogen roadmap, when companies are working with government to make it happen. The bigger problem as well is the budget is not well done because you don't actually know how much it's going to cost. So better techno-economics before the project, which the problem you have is you can only make them more accurate once you've done the project at least once, will help. It's usually when you find out, well, the project was 5 million, it's going to cost 50 million, then the investors pull out right away. And if you've started the project, it's too late. You have to keep going. So the bigger part is finding out how much it's actually going to cost and how long, and also how long it will take. Right? A lot of hydrogen, even fuel cell labs that I've seen in Europe that are running large scale, They are in the middle of nowhere because of the safety aspect of consuming a huge amount of hydrogen. And so legislation on hydrogen project is an insanely big topic of like people who have emerged, skills that have emerged in the last 3 years, or people who are like, well, you want to make this project, hey, you can't do it next to a town because you're going to blow up the town. That people are never going to agree with that. And that's something that you don't think about when you just build it on paper and you just do your design of this plant. So all this plays a part in it and keeps on changing.
I think another message, when you mentioned, like, for instance, transporting hydrogen,
Yeah.
it's ridiculous
Yeah.
to use trucks and diesel
Yeah.
To transport
The hydrogen
for
a car. Yeah.
Yeah, so the whole life cycle that you learn in your courses.
Yeah.
So now we are basically in the process of planning for the Western Sydney Airport, the
Yeah.
new airport in Western Sydney. And just imagine for basically the jet fuel transport. Right now in Kingsford, Kingsford Airport, basically the depot for the jet fuel is located at port and is through the pipeline that
Yeah.
it goes to airport. Now we don't have any pipeline for the Western Sydney, so it's estimated that there will be 500 trucks
A day.
a day actually transporting
Yeah.
fuel,
Yep.
fuel jet to
It's going to be interesting.
Sydney, Western Sydney Airport.
Making fuel, making CO2 all the way there, all the way to get there and everything. Yeah.
And then we had this discussion that, but then, okay, if we basically build pipelines for Western Sydney Airport, then would it be retrofitted for hydrogen
Yeah.
ammonia in future? Because we know that in 10 years, we will not really have, kind of like
Yeah.
the jet fuels
Yeah.
for these airplanes, so
Yeah.
they should be decarbonized.
Yeah.
And then in that situation, then we need ammonia or
Hydrogen.
hydrogen for the pipeline,
Yeah.
but the pipeline is suited for,
Yeah. Whether it can do it or not, it's not even sure. Yeah.
so in terms of like cracks for the pipelines, etc.
It's
How
insanely
about the
complex.
storage tanks? Should
Yeah.
we put the storage tanks? Should we build storage tanks for in Western Sydney Airport for the fuel jet,
Yeah.
or no? In 10 or 10
Yes,
5 years, it
will
will
be
be
gone.
phased out
Yeah.
because of
Yeah.
hydrogen.
Yeah.
So again, there are so many.
It's insanely
engineering
it's
aspects.
awfully complex. It's really fun.
And I read one of the KPMG's reports on
Yeah.
Western Sydney Airport. It's just, the figures.
They're pretty pictures.
I'd rather actually not comment, but you get the gist of it.
Yeah.
Okay, great. So I hope that you enjoyed today's lecture. I certainly enjoyed. So these guys actually had workshop at 9.
Okay.
You should be tired now.
Yeah.
So we leave you to it, and thank you so much. Okay, can we have a group photo with Quentin?
Oh yeah, please. Yeah. And if you guys ever want work experience, we can't pay anyone, but we can welcome anyone who wants to join us. We don't bite until you say yes.
Just the first slide.
Yeah.
I really like group photos with my
Yeah.
students, and
Yeah, that's cool.
I know, because it's the memory, right?
Yeah, I agree.
Basically, I have a collection of.
Yeah.
Right, awesome. So guys, photo,
Selfie or photo?
selfie. Yeah.
Yeah.
And once.
You need to be on the photo as well, though.
We will get one selfie as well.
Okay, sure.
For me, it's just the memory of you guys is important.
Yeah. Well, last time it was only four of you, so this is double compared to last year. It was 9 a.m. though.
Okay, so maybe I can actually come a bit closer. Lighting is a bit strange, but I think here. Let's see if I can fit you all. Yes, that's good. That one is very bright, glary, but that's
It's okay.
okay. Great. Ready? 1, 2, 3.
Hydrogen.
That was good. And then let me see if I can.
Thank you. Thanks for having us. It was fun.
Thank you.
Yeah, thank you. Thank you so much. Okay, see you Tuesday next week. Yay. Thank you, Quentin.
Of course, it was fun. I like doing this one because it's so much on the on the economics.
Honestly, yeah.
Merci beaucoup pour la leçon. C'était
Merci.
très intéressant.
Merci. Yeah.
Merci beaucoup.
Merci.
À la commence de la leçon, j'ai entendu ton accent. Je
Oh yeah.
Est-il
Yeah.
français?
Absolument, oui. Yeah.
Bonne journée.
Merci.
I'll show you photos.
Yeah, please. Yeah.
Post it, post it.
Will do.
It was
Yeah.
fantastic.
Yeah, thank you. Thank you very much.
Awesome.
Have a good day. I'll show you a photo of the drone as well.
Yes.
Yeah. Oh, wait. I was just gonna sit it. I can just shout them.